This is MT101. This course is the course title is General Mathematics, and this is the first tutorial. General Mathematics covers topics from college algebra. The book that we'll be using, which is an electronic book, has the title College Algebra Essentials by Julie Miller. We will not have a hard copy. You will have to use the soft copy, which is provided by Connect. You can access it from the LMS. The chapter R, which is R stands for review, reviews the basic material that we will be using. These are things that mostly you should know that you have covered in high school. All of these things that we will cover are important. You have to make sure that that you understand this chapter, because we will be using the material from chapter R and the remaining topics in this course. First, we will have a quick review of sets and the real number line. Of course, in this course, we'll be working with real numbers, quite a bit. Some of the basic sets of real numbers we should know, and also we'll talk some about the real number line. The first set we will look at is the set of natural numbers. We use bold N to describe the set. These are the counting numbers, 1, 2, 3. This is, of course, this set continues. These three dots means that the set continues to infinity. 1, 2, 3, 4. This is an infinite set. The next set is a set of whole numbers. We use W for that. This is basically the set of natural numbers, but we add 0. So you start with 0, 1, 2, 3. And that also continues. This is also an infinite set. The third set is the set of integers. We use a bold Z for that. This is all the whole numbers plus the negative numbers. The whole numbers is a subset, 0, 1, 2, 3, and that continues. And also the negative numbers, negative 1, negative 2, negative 3, and that continues to negative infinity. The set of rational numbers, we use Q for that, is the set of fractions. Any number that can be written as a fraction, it has the form P over Q, where P and Q are integers, and Q does not equal 0. We cannot divide by 0, so any fraction will have this form, P over Q, with Q does not equal 0. Then we have the set of irrational numbers. Of course, any real number is either a rational number, and if it's not a rational number, then it will be an irrational number. There are many examples of irrational numbers. You can think of pi, the number e, and many numbers that are irrational numbers. But in general, any number that's not rational will be an irrational number. Also, we will be using the absolute value. Here is a definition of the absolute value. So for any real number x, the absolute value of x, we use vertical bars. X is between two bars. This means the absolute value of x. This is equal to x if x is greater than or equal to 0, and equal to negative x if x is less than 0. If the number is 0 or larger than 0, you take the number like it is. If the number is negative, you change the sign. The absolute value of a number is always either 0 or a positive number. And here is a definition of the distance between any 2 points, any two real numbers. The distance between any two numbers a and b is just the absolute value of a minus b, and that's just the same as the absolute value of b minus a. This is the distance between points a and b. Here are examples of the things we covered so far. 2 over 3 is an element of Q. طبعا this symbol here that looks like the letter E means that this element 2 over 3, this number, belongs to the set of rational numbers. 2 over 3 is an element of the set of rational numbers. Minus 2 does not belong to n. Minus 2 is not a natural number. The third notation is using the subset notation. Z is a subset of Q. That means every integer is considered to be a rational number. Any integer a can be written as a over 1, so you can think of an integer as a rational number. Of course, this subset notation, Q is a larger set. Z is a subset of Q, but Q is larger. There are rational numbers that are not integers. The other thing we need to be familiar with, because we will use it a lot, is the interval notation. There are more than one way to represent an interval. Here is an example, many examples. One way to represent an interval is using set builder notation. In this notation, you define the set, for example, x, such that x is less than 3. This is a set of all numbers that are less than 3. And here 3 is not included. If you want to describe this interval using a graph, you draw the real number line, start with 3, use round bracket to indicate that 3 is not included, and then highlight all the numbers to the left of 3 are included in the interval. The other notation that we use a lot is using the interval notation. Use a round bracket to indicate that the endpoints are not included. You start with minus infinity, comma 3. This is the set of numbers less than 3, and of course will be greater than minus infinity. All the numbers to the left of 3. Here is another interval which has one of the endpoints, x, such that x is larger than minus 2 and less than or equal to 5. This interval does not include minus 2, but it does include 5. It's all the numbers between minus 2 and 5, and it includes the number 5. When you draw a graph for that interval, use round bracket with minus 2, use square bracket with 5 to indicate that 5 is included in the interval. And of course, the blue line represents all the numbers between minus 2 and 5. Minus 2 is not included, 5 is included. In interval notation, start with a round bracket for minus 2, then comma 5, and end with a square bracket that indicates that 5 is included, but minus 2 is not included in the interval. Here is an example of using the absolute value to calculate the distance between 2 points. The absolute value of 2 minus the square root of 7 is equal to, we look at this, what is the result of 2 minus the square root of 7? Since the square root of 7 is larger than 2, this number is negative. The absolute value of this number will be negative 2 minus the square root of 7. Again, this is true because the number in between the absolute value bars is negative. The absolute value of a negative number, you change the sign and you take the negative of the number. But this is minus 2 minus the square root of 7. We can write it without the negative here. This will be negative, the square root of 7 is just plus the square root of 7 minus 2. This distance, of course, this is absolute value, but this is a positive quantity. Here is another example of calculating the distance between two numbers. The distance between 6 and minus 4 on the number line is the absolute value of 6 minus minus 4. Minus 4 is plus 4, so this is the absolute value of 10, which is equal to 10. Of course, the same distance can be measured, taken -4 minus 6, which is the absolute value of -10, which is equal to 10. You get the same distance. Example 5 is important because here we are reviewing the order of operations. When we work with real numbers, there are operations such as addition, subtraction, exponents, raising a quantity to a power. It is important that you know how to do these operations in the correct order. If you don't apply the correct order for operations, you will get the wrong answer. Make sure that you know the order of those operations, and the book has plenty of exercises. This is something that you should already know. If you don't remember, then you should probably do more examples. So here is an expression, an algebraic expression that involves many operations. We want to simplify, meaning we want to get a final answer, and it simplifies the expression. We should end up with a solution or a result for this expression. Starting with the expression, the first order of business, this is the expression we started with. The first thing we should do is anything within brackets you should apply first. This is a bracket here, 5 minus 8. Also, the radical, you can think of the radical as a quantity raised to the power 1/2. Anything within brackets or under a radical should be applied first. 5 minus 8 is equal to -3, and we have squared. This expression now is 12 minus 2. 5 minus 8 is just -3 squared. Under the square root, 5 squared is 25. 4 squared is equal to 16, so it's -16. The next operation you should apply is the exponents, or the power. -3 squared means -3 times -3. This should equal to 9. 25 minus 16 is 9. Then the next step you apply now multiplication. 2 times 9 is -18. The square root of 9 is equal to 3. Now you have minus and plus. These have the same priority. 12 minus 18 is -6, plus 3 is equal to -3. This expression will simplify to -3. If you apply the operations in any order, and if you don't apply the correct order, you will not get -3. Make sure you know how to apply the operations in the correct order. We will use this not just when we work with numbers, but when we are working with equations, when we are trying to solve equations or simplify algebraic expressions. It is important to know the correct order of operations. Now about the sets that we discussed before. All of these are sets of real numbers. Basically, this big rectangle represents all real numbers. You have two rectangles. The one in the left represents the rational numbers. The rectangle to the right represents the irrational numbers. These are disjoint sets for any real numbers, either a rational number or it is an irrational number. The rational numbers, here in this pictures, they show it as the smaller of the rectangles, but it's actually a very large set. It's an infinite set. For any irrational numbers, any number that's not a rational number will be an irrational numbers. It includes, for example, non-terminating and non-repeating decimals. There are also numbers, then the number pi is considered to be an irrational number. Most square roots will give you an irrational numbers. For example, the square root of 19 will be an irrational number. And normally, if you write an irrational number as a decimal, then it will have a non-ending representation. These numbers continue. Now, a rational number, as we said before, is any number that can be written as a fraction. There are many examples. For example, 1.62 is a rational number. You can think of this as 162 divided by 100. 2 over 7, 1.437. These are all examples of rational numbers. Now, as a subset of the rational numbers is a set of integers. These are the whole numbers, the positive and negative numbers. A subset of the integers is a set of whole numbers. And طبعا a subset of the whole numbers is a set of natural numbers. This is the relationship between the sets. You should be familiar with all these sets. We will be working with different sets of real numbers. So you should know the different sets and the notation we use to refer to these sets. Section R2, we will look at algebraic expressions and properties of real numbers. These properties is something that we use. All these properties deal with the different operations. Anytime you have an algebraic expression, it will have addition, multiplication. But we will just quickly review some of these properties. This is something we know about real numbers. First of all, a property of addition is called the commutative property. That means a plus b, you get the same number as if you add b plus a. Same thing, you have a commutative property for multiplication. A times b equals b times a. The associative property, if you are applying addition, if you're adding three numbers, you can add a and b first and then add c. You get the same thing as if you add a to the sum of b and c. In fact, you don't even need brackets. You can add the numbers in any order you want. The associative property tells you you get the same result. The associative property for multiplication is a times b times c, and if you multiply a and b first times c, you get the same thing as a times the product b, c. Identity means a number that if you apply to any other number, you get the same number. There's two identities, identity for addition and identity for multiplication. The identity for addition is 0. For 0 added to any number, you get the same number. A plus 0 equals a, and 0 plus a is equal to a. The identity for multiplication is 1. If you multiply 1 by any number, you get the same number. A times 1 is equal to a, and 1 times a is equal to a. There is the inverse property. The inverse here means another number you add to the number to get the identity. So for addition, the inverse of a is minus a. For the inverse property, a plus minus a or negative a, you get 0. Of course, negative a plus a is equal to 0. The inverse for multiplication is a number that you multiply the number by to get 1. So it's just the reciprocal of the number. Each real number will have an inverse except 0. For the inverse of a is just 1 over a. When you multiply the inverse, 1 over a times a, you get 1. For a times 1 over a is 1, and 1 over a times a is equal to 1. This works for all numbers except the number 0. The number 0 does not have an inverse. The final property relates both multiplication and addition, and it's called the distributive property. Here we say that multiplication distributes over addition. For a times b plus c is equal to a times b plus a times c. If you add those two numbers, b plus c, and then multiply a, you get the same results as if you take a times b plus a times c. This is called the distributive property, or that multiplication distributes over addition. The next thing we would like to do, because algebra deals with symbols and how to handle them, an algebraic expression normally would have variables, symbols, plus the operations that we discussed. One of the things we use algebra for is to write a formula. A formula relating two or more variables is one type of a mathematical model. Anytime you use mathematics in real life, we call this a model. So a model can be even a formula or an algebraic expression. We will take an example. One is just an example where algebraic expression, or in this case a formula, is being used. We will see many other formulas in the remaining topics of the book. For example 1, we have in a province in Canada, place in Canada, an individual caught speeding. You know, when you drive a car, if you drive over the speed limit, you might get a ticket. In this ticket, the fine that you pay depends on how fast you are going over the speed limit. In this particular place, if you are caught speeding between 31 and 50 kilometers per hour over the speed limit, you pay $70 as a surcharge. This is a fixed charge, plus you pay $2 for each kilometer over the speed limit. This is the minimum charge you will pay, $70, plus $2 for each kilometer over the speed limit. Now, this is a real life situation. To use a formula, first of all, you have to decide what the formula is for. We want a formula that will tell us how much the person will be paying, how much is the ticket. That depends on how fast the person is driving over the speed limit. Here is where algebra comes. These are variables. The amount of money you pay is a variable, and so is the speed over the speed limit. You need to start by giving names, or give names to the variables. The first variable is cost, the cost of the ticket. We will call this capital C, and that the cost here is in dollar. The other variable is how fast the person is going over the speed limit, and that we will use X. X represents the number of kilometers over the speed limit. Now the cost will be C is equal to 70, that's the minimum charge, plus 2 times X. X here is the number of kilometers over the speed limit. For each kilometer you're paying 2. For the amount you pay over the 70 is 2 times X. Here is my formula. It has two variables, X, the number of kilometers over the speed limit, and C is the cost, which is, we said this will be in dollar. This is a formula that gives us the cost in terms of the speed over the speed limit. We will see how to use the formula. In real life, how do you use a formula? We want to use the model we just did to determine the cost of a speeding ticket for an individual traveling 40 kilometers over the speed limit, over the posted speed limit. Here is our model. Here is our formula. C equals 70 plus 2x. How do we calculate the cost? Well, what is x? X is 40, because the person is traveling 40 kilometers over the speed limit. What we do to use the formula is replace x by 40, and you substitute 40 for x. Now C is equal to 70 times 2 times 40. This is 70 plus 80. This is equal to 150. That's how much the person will pay. This is the cost of the ticket for a person traveling 40 kilometers over the speed limit. The next set of rules that we would like to review, which are also important, is the exponents, integer exponents and scientific notation. طبعا integer exponents, that means the exponent will be an integer, either positive or negative. First of all, to raise a number to a power, you have to start with a positive number. يعني b here, which we call the base, and you raise it to an integer. طبعا again, that's one of the things that we should know from high school. To raise a number to a positive integer, that means you multiply the number by itself that many times. And b squared means b times b. B cubed is b times b times b. And we will also define what it means to raise a number to the 0 power, and also we'll see what a negative power means. The first case, b to the 0 equals 1. This is by definition. And if you take b, the base, which is a positive number, raise it to the power 0, you always get 1. This is regardless, of course, what the base is. Now, what does it mean to raise a number to a negative power, yani b to the minus n? It means, or it equals to 1 over b to the n. Yani, for example, b to the power minus 2 is just 1 over b squared. We will see examples for all of these rules. Now, more of the rules that we will use. The product rule for exponents. طبعا you multiply two numbers that have the same base. So b to the m times b to the n is just b, and you add the powers, m plus n. When you divide, yani the quotient, you subtract the power. B to the m divided by b to the n is equal to b to the power m minus n. طبعا start with the power of the numerator minus the power of the denominator. The next rule is called the power rule for exponents. B to the m and everything raised to the power n is equal to b to the power m times n. Yani you multiply the outside power with the inside power. The power of a product, and if you have a times b and everything raised to the power m, this is the same as a to the m times b to the m. For example, ab to the power 2 is equal to a squared times b squared. The power of a quotient, a over b raised to the power m, is equal to a to the m, yani the numerator to the power m, divided by the denominator to the power m. A to the m divided by b to the m. We will see examples of all of these rules, and you should know them because we will use them a lot. The other topic we will cover here is called the scientific notation. This is just a way to express numbers. The way that you express a number in scientific notation is you want to write the number as a times 10 to the n. Yani here a must be a number such that the absolute value is greater than or equal to 1 and less than 10, and طبعا for some power of n. N is an integer and could be positive, negative, or 0. Whenever you take a number and write it in this format, this is called scientific notation. This is the other topic that we will look at, which relates to powers or exponents. Here are examples. Minus 4p raised to the power 0 is equal to 1. طبعا here this quantity is positive. Raise it to power 0, you get 1. W raised to the power minus 6 is the same as 1 over w to the power 6. Here are examples about the rules of product and quotient. B to the m times b to the n is equal to b. And you add the powers m plus n. For example, x to the 7 times x to the minus 2 is equal to x, and add the powers 7 plus minus 2, you should get x to the 5. With divisions, of course, you subtract the powers. For example, z to the power 9 divided by z to the power 5 is z to the power 9 minus 5, which is z to the power 4. The next rule, if you have b to the m, everything raised to the power n is equal to b, and multiply the outside and inside power. For example, y to the power minus 2 and everything raised to the power 4 is equal to y, and multiply 4 times minus 2, you get minus 8. This is a number with a negative exponents. You can always write it as 1 over y to the 8. Next rule, the power of a product, ab raised to the power m is a to the m times b to the m. Here is an example. 2x raised to the power 4. 2x is just 2 times x. So you can write this as 2 to the 4 times x to the 4. 2 to the 4 is just 16. So you have 16 times x to the 4, which is just 16x to the power 4. For division, a over b raised to the power m is equal to a to the m over b to the m. Here is an example. 5 divided by x squared, everything raised to the power 3, is equal to 5 to the power 3 divided by x squared to the power 3. 5 cubed is equal to 125. For the denominator, you have to multiply the powers 2 and 3, so the result should be x to the power 6. Now again, the next topic, which is related to the exponents, is scientific notation. I'm sure all of you have seen scientific notation. Then most calculators, the default display, if you do any calculations, you will see the result in scientific notation. So what is scientific notation? As we defined it before, you write the number as a number, which is less than 10 and greater than 1, multiply by some power of 10. For example, 54,000. The way to do this is think of the decimal to the right of the 0. How many times you have to move the decimal to get a number less than 10? Well, you can move it 4 places to get 5.4. Since you moved it 4 times to the left, you multiply by 10 to the 4. So 54,000 is equal to 5.4 times 10 to the 4. This number is between 1 and 10. Multiply by a power of 10. This is the scientific representation of 54,000. Notice, because this number has 5 digits to the right of the decimal, the power here is positive. If you have a number less than 1, then you will get a negative power of 10. For example, 0.00, there is 9 zeros here, 0, 0, 0, 0, 0, 0, 0, 0, 0, 5, 6, 8. This is a very small number. Here, to get a number between 1 and 10, you have to move the decimal to the right. And you need to count how many places you move the decimal. You actually have to move the decimal 10 places to get 5.68. When you move the decimal to the right, it's like you multiplied by powers of 10. So then you divide by the same power. So it's like multiplying by a negative power of 10. We move the decimal 10 places. So this is 10 to the minus 10. When you move it 10 places, you get 5.68. That's A. And then since we moved to the right 10 places, the power of 10 should be minus 10. By the way, if you start with a number that is already between 1 and 10, you can just write it as the number itself times 10 to the 0. The number 6, you can write it as 6 times 10 to the 0. That would be the scientific notation. Also, using scientific notation, you should be able to carry out products. So here are two numbers written in scientific notation, and we'll see how to multiply them. You have 2.5 times 10 to the 8, that's your first number in scientific notation, times the second number is 6 times 10 to the 3. You multiply them, like you multiply two brackets, you can multiply the numbers 2.5 times 6 and then multiply the power of 10 together. This is using the associative property. So this becomes now 2.5 times 6 times 10 to the 8 times 10 to the 3. The product here, 2.5 times 6 is just 15. 10 to the 8 times 10 to the 3 is 10 to the 11. Now this result is correct, but it's not in scientific notation. Then 15 is larger than 10. But you need to write this as 15 can be written as 1.5 times 10 to the 1 times 10 to the 11. The final result is 10 to the 1 times 10 to the 11 is just 10 to the 12. Now you have the result in scientific notation. This is A, this is a number between 1 and 10, multiplied by 10 to the power 12. In section 4, we will talk about rational exponents and radical. Anytime you have a rational exponent, meaning the exponent is a fraction, the result will give you a radical. Starting with the definition of the nth root, we say that b is the nth root of a if b to the n equal to a. For example, you can say 3 is the square root of 9 because 3 squared is equal to 9. Now when you use the symbol for the radical, when you write the nth root of a, represent the principal nth root of a. Meaning if there is 2 square roots, for example, if n happens to be even, you may have 2 square roots. Whenever you use the radical symbol, you should take the principal nth root, meaning the positive square root. If n is greater than 1, the definition of a radical, we don't take n equal 1, we start with n greater than 1. This is an integer. The nth root of a is a real number. Then here is a way to define a radical exponent or rational exponents. The a to the power 1 over n equals to the nth root of a. N here is called the index. The denominator defines the index of a radical. The a to the 1 over n is equal to the nth root of a. For example, a to the 1 over 2 is the square root of a. A to the 1 over 3 is equal to the third root or the cube root of a. Now this is the special case where the numerator is 1. Here is the general case. If you raise a to the power m over n, the denominator still defines the index of the radical. But this is a to the m over n equal to the nth root of a and everything raised to the power m. Or you can just leave the m inside the radical. Yani this is also equal to a to the m over n is equal to the nth root of a to the m. Either, in both cases you take the nth root, the denominator defines the index of the radical, but the numerator, you can either leave it outside or you can write it inside. And we will look at examples of this case. Now we did say in whether n is even or odd, you may have more than one nth root. If n is greater than 1 and a is a real number, if n is even, you may have 2 roots, but every time you use this square root or the nth root symbol, you should take the positive nth root. For the nth root of a to the n is equal to the absolute value of a. For example, the square root of a squared is the absolute value of a. The cube root of a to the power 3 is the absolute value of a. This is when the case is even, you make sure you take the absolute value of a. If n is odd, you don't have to worry about it, so you can just write the nth root of a to the n is equal to a without the absolute value, because in this case there's only one nth root. Here are some quick rules that follow from the rules of exponents. The nth root of a times the nth root of b is equal to the nth root of ab. And you can write the product of radicals. If they have the same index, you can write it as one radical. For quotient, the nth root of a divided by the nth root of b is equal to the nth root of a over b. The final property is called the nested property of nested radical. The mth root of the nth root of a is just the m times n root of a. Yani the index is equal to the product of the two indices. For example, the square root of the cube root of a is the sixth root of a. Yani multiply the two indices. Now here are some examples. 7 is the square root of 49 because 7 squared is equal to 49. But also minus 7 is a square root of 49 because minus 7 squared is equal to 49. But when you use the square root symbol, you take the positive square root. For the square root of 49 is always 7, equal to 7. 7 is greater than 0, and 7 squared is equal to 49. With odd indices, there's only one root, so you don't use the absolute value. Here is the minus 64 raised to the power 1 over 3. This is the cube root of minus 64, which is minus 4. Notice now for even indices, you cannot apply an even index to a negative number. For example, you cannot take the square root of minus 64 or the fourth root. Even indices cannot be applied to negative numbers. with odd indices, it's okay to apply it to a negative number, like the example we just saw. Now, for example, if we take minus 16 to the power 1 over 4, this will be undefined, because this will be the fourth root of minus 16. 4 is an even number. You cannot take an even index radical of a negative number. Here is an example where the power is a fraction. 125 raised to the power 2 over 3. Remember that 3 determines the index. So this is the cube root of 125, everything squared, or you can take the cube root of 125 squared. It's easier to do it this way. The cube root of 125 is just 5. You square everything, so you square 5. The result will be 25. Using the rules of exponents, you can combine this with the rules for radicals. You can simplify some expressions by applying the rules for exponents. This is example 3. Starting with x to the power 1 over 5 times x to the power 2 over 5 divided by x to the power 4 over 5, everything raised to the power 10. Start by trying to simplify what's inside the bracket. First, add the two powers. You get x to the power 3 over 5 divided by x to the power 4 over 5. Then subtract the powers, simplify the quotient. So you subtract the powers in this case, so the result will be x to the power 3 over 5 minus 4 over 5, and everything is raised to the power 10. This 3 over 5 minus 4 over 5 is just minus 1 over 5. When you raise it to the power 10, you multiply 10 times minus 1 over 5. The result should be minus 2. The result is x to the minus 2. And this is a negative power. You can always write it as 1 over x squared. Here are more examples that relates to the rules we just looked at. The sixth power of y to the 6 is equal to the absolute value of y. That's because the index is even. But the fifth power, the fifth root of y to the 5 is just equal to y. You don't need the absolute value in this case. Now also you can simplify radicals. For example, the cube root of x to the 13. 13 is not divisible by 3. But you can write the 13 as x to the 12 times x, and now distribute the cube root. So this should equal to the cube root of x to the 12 times the cube root of x. The cube root of x to the 12 is just x to the power 12 over 3, which is x to the 4. And there is nothing you can do with the cube root of x. So this is your final answer. The trick here is to break up if the power is not divisible by the index. You can write it as the product of two things, and at least one of them, the power should be divisible by the index. Here is a problem that uses the division of radicals. This is the cube root of 2x to the 4 divided by the cube root of 16x. Now you can write them under the same radical. This is the cube root of 2x to the 4 divided by 16x. You can cancel out the common factors. Cancel the x from both numerator and denominator, and cancel the 2. You should get x to the power 3 divided by 8. Now you can distribute the cube root over the numerator and denominator. This should equal to the cube root of x to the power 3, which is just x, divided by the cube root of 8, which is just equal to 2. Here is my final answer, x over 2. Here is a property of the nested roots. The fifth root of the cube root of x is equal to the 15th root of x. This is just multiplying the two indices. 5 times 3 is equal to 15. This is the 15th root of x. Here is another example of simplifying expressions using these rules. The cube root of 4x squared times the cube root of 6x. We can write them under the same cube root by multiplying. But this is equal to the cube root of 4x squared times 6x, which is equal to 24x to the power 3. Now you can write this as x squared times 24x and apply the you can write it as 20. This is just 24 times x to the power 3. This is equal to the cube root of 24 times the cube root of x to the power 3, which is just x. Now also the 24 can be written as 2 times the final answer. When you factor the x cube, you get x, and 24 is just 3 times 8. The cube root of 8 is just 2, so your final answer should be 2x times the cube root of 3. Here is another one. You're adding radicals. Each term here has a radical, so you can try to simplify each term and then add similar terms. For the square root of 3x squared plus x times the square root of 12x minus 5x times the square root of 3x. Here you can write this as x squared times 3x and apply the square root to x squared. So you can just write it as 4x times the square root of 3x. For this one, you can write this as 4 times 3x and apply the square root. So this is 2x times the square root of 3x. There is not anything you can do with the third term, so just leave it like it is. But now you notice you have a common factors to the three terms, which is the square root of 3x. Take it as a common factor. Also, x is a common factor. Factor x times the square root of 3x. From the first term, you're left with 4. From the second term, you're left with 2. From the third term, you're left with minus 5. 4 plus 2 minus 5 is just equal to 1. The final result will be 1 times x times the square root of 3x. The final result is x times the square root of 3x. Section 5, we will discuss polynomials and also we will see how we can multiply radicals. The definition of a polynomial. A polynomial in one variable is an expression. It's an algebraic expression. It consists of real numbers multiplied by powers of the variable x. So you have an times x to the n plus a n minus 1 times x to the n minus 1. The last term is a0. This is the term that's multiplied by x to the 0, to the power 0. So it's basically terms. Each term is just a number. We call it the coefficient, times multiplied by a power of x. And we notice here that a polynomial is written in a way that you start with the highest power and then the next power until you reach the 0 power. The coefficients that are multiplied by the powers of x, the coefficients an minus 1, these are real numbers. The leading coefficient, that's the first coefficient, the coefficient of the first term, the highest power, cannot be equal to 0. The exponents, n minus 1, all of these are whole numbers. They're actually positive integers. The term an x to the n, that's the first term, the term that has the highest power, is called the leading term. The coefficient of that term, a to the n, a sub n, is called the leading coefficient. The degree of the term is the sum of the exponents on the variable factors. Of course, we are only considering polynomials of one variable, so the degree in this case will be the power, the highest power. So it's the power of the leading term. We'll look at examples. Of course, to be able to tell the power or the degree of the polynomial, it must be written in the form where the powers of x are written in descending order. Let's look at this polynomial, 9 times x to the 5 minus 5 times x to the 7 plus 3x minus 4. We notice that this expression, the powers are not ordered. X to the 5 comes before x to the 7. So what we need to do is reorder the terms. So we can write this as minus 5 times x to the 7 plus 9 times x to the 5 plus 3x plus minus 4. We notice in this polynomial some of the powers are missing. There is no power 6 or power 4. So in this case, the coefficients for these terms are 0. In this polynomial, the leading term is minus 5 times x to the 7. The leading coefficient is equal to minus 5. The degree of the polynomial is equal to 7. We will not be considering polynomials of more than one variable, so we just can omit this last statement. Next, we would like to see how we can add and subtract polynomials. We do this using or treating the polynomial as algebraic expression, so we can add polynomials just like we add algebraic expressions, and the same thing for subtraction. Here is an example. Here is the first polynomial, 7x squared minus 3x plus 6, minus the second polynomial is 2x squared minus 8x. The way to do this, of course, is we write this first term without the brackets. Then for the second term, since there is a negative in front of the bracket, we change the signs. So the result now will be 7x squared minus 3x plus 6. That's the first polynomial. طبعا adding the negative term will be like 6. The minus 2x squared here will be just minus 2x squared. And then also minus 8x will be plus 8x. The final step, what we would like to do is add similar terms. 7x squared plus minus 2x squared is just 5x squared. Minus 3x plus 8x is 5x, and then plus 6. Subtracting one polynomial from another, the result will be another polynomial. In this case, this is a polynomial of degree 2. The leading coefficient is 5x squared. The leading term is 5x squared, and the leading coefficient is equal to 5. Of course, this is an example of subtraction. Addition is handled similarly. You add two polynomials like you add two algebraic expressions. Next, we would like to see how to multiply polynomials and also, in general, how to multiply algebraic expressions. So here is a product of two polynomials in y. We want to multiply 3y minus 4 times 2y plus 5. The way to do this is take each term in the first polynomial, multiply it by each term of the second polynomial. Starting with 3y times 2y gives us 6y squared. 3y times 5 is 15y. Then minus 4 times 2y is minus 8y. Minus 4 times 5 is equal to minus 20. Next, we add similar terms. So we have 6y squared. Then 15y minus 8y is just 7y minus 20. The result of multiplying two polynomials of degree 1 is a second degree polynomial, 6y squared plus 7y minus 20. The next example, these are not polynomials, these are just algebraic expressions. So we'll see how to multiply this. This is multiplying 2 times the square root of x times 3 the square root of x plus 5 times the square root of z minus 4. And this is not a polynomial, but we can still multiply algebraic expression. The way to do this is you multiply the outside term by each term inside the bracket. Multiply it by the first term, then also multiply it by the second term, and multiply it by the third term. The first multiplication, 2 times the square root of x times 3 square root of x. Here, this is 2 times 3, which is 6, and then the square root of x times the square root of x is just x. Multiplying the second term, the middle term, you have 2 the square root of x times 5 the square root of z. 2 times 5 is 10. The square root of x times the square root of z is just the square root of xz. The third term, multiplying 2 the square root of x times minus 4, we will get minus 8 times the square root of x. Again, this is not polynomial multiplication, it's just multiplying algebraic expressions. There are some formulas that will help us multiply certain algebraic expressions. These are special cases or special products. The first formula, which is all of these formulas are useful, and we will use them when we are simplifying expressions. If you multiply a plus b times a minus b, first you notice this is the same expression. The first bracket is the same as the second bracket. The only difference is the sign. This is plus and this is negative. The result will always be the square of the first number, which is a squared, minus the square of the second number. You can try to multiply those two terms, and you will see this formula is correct. Anytime you multiply a term a plus b times a minus b, the result will always be a squared minus b squared. The second formula shows us how to square a bracket. A plus b squared is equal to the square of the first number, a squared, plus 2 times the first times the second, 2ab, plus the square of the second. The third formula is very similar to the second formula, except you have a negative. You have a minus b squared. The result will be the square of the first, a squared. Now, because of the negative, the middle term will be minus 2ab, plus the third term is just b squared. These three formulas are used a lot. and you really should know, you should remember these formulas because they will be useful to simplify expressions. Here are examples for each of these formulas. 2x plus 7 times 2x minus 7. We can use the first formula. The first bracket is the same as the second bracket. The difference is just on the sign, plus and minus. So the result should be the square of the first, yani 2x squared, minus the square of the second, yani minus 7 squared. 2x squared is just 4x squared, and minus 7 squared, which is just minus 49. The second example, we will illustrate the second formula. For 3x plus 2, everything squared, you take the square of the first term, yani 3x squared, then 2 times the first term times the second term, yani 2 times 3x times 2, plus the third term will be just 2 squared, yani the second term squared. This is just 9x squared. Then 2 times 3x times 2 is just 12x, and 2 squared is just equal to 4. An example using the third formula, if you take 5 times the square root of x minus 3, everything squared, this is equal to the square of the first term, yani 5 times the square root of x squared, 2 times the first times the second, yani 2 times 5 the square root of x times 3. Remember now this is negative because of the negative sign. The third term will be just 3 squared. Next we want to expand these brackets. For 5 the square root of x, everything squared, will equal to 5 squared, which is 25, times the square root of x squared, which is just x. The middle term is minus 2 times 5 the square root of x times 3. If you multiply the numbers, you should get 30 times the square root of x. The third term, 3 squared, is just equal to 9. Now, in section 6, we'll look at factoring. In the previous section, we were multiplying things. In section 6, factoring, you take an algebraic term, try to write it as a product of factors. There are, depending on the expression, there are different ways to factor, but here is the general strategy. These steps will work depending on the term that we are trying to factor. First, you may try to find the GCF. This is the greatest common factor. If you have an expression, see if the terms of that expression have a common factor and try to factor the greatest common factor. The other thing you might want to do, depending on the expression, identify the number of terms. You look at the expression you're trying to factor and see how many terms it has. There is 2 cases that we will look at. If you have 4 terms, try to group the factors. If you don't find the common factors to all the factors, try to group them. So in the case of 4 terms, factor by grouping 2 terms with 2 terms or 3 terms with 1 term. If you have 3 terms, then see if the expression can be factored using one of the special formulas that we looked at. See if you have a perfect square, a trinomial, meaning you have 3 terms. See if you can write it as a perfect square. See if you can write it as the square of a bracket. One of the cases, like if you have a squared plus 2ab plus b squared, you can write it as a plus b squared. And this is exactly the formula we looked at a while ago. That a plus b squared is equal to a squared plus 2ab plus b squared. So if you have a trinomial that has this form, you can certainly write it as a plus b squared. This is factoring because you have written this expression as a plus b times a plus b, or a plus b squared. The other case, if you have a squared minus 2ab plus b squared, then you can write it as a minus b squared. طبعا in some cases, if you cannot do this, you can factor by trial and error, and we will see طبعا examples of how to do this. You always طبعا try to يعني apply the most straightforward method. If one method doesn't work, you can try another method to factor the expression. If you have two terms, see, طبعا in this case this is called a binomial because you have two terms. See if it fits one of the following patterns. طبعا again, this is using the formulas we already covered. If the two terms has this form, يعني the difference of two squares, a squared minus b squared, you can always factor it by writing a plus b times a minus b. And I hope that you recognize this as the formula we looked at. We know that a plus b times a minus b is equal to a squared minus b squared. So if you have an expression of this form, the difference of two squares, you can write it as a plus b times a minus b. If you have the sum of two cubes, if you have a cube plus b cube, you can write it as a plus b times the square of the first variable, a squared, minus ab, which is a product, plus b squared. طبعا you can check to see if the product of a plus b times a squared minus ab plus b squared will give you a cube plus b cube. It will. You can always factor the sum of two cubes in this manner. What about the difference of two cubes? If you have a cube minus b cube, you can factor it as a minus b. Notice the difference here is only in the sign. To factor a cube minus b cube, you can write it as a minus b times a squared plus ab plus b squared. Notice the previous one, a cube plus b cube, you're starting with a plus b, so the sign is the same. But the sign of the middle term is negative. For the third formula, a cube minus b cube, the sign here is the same, يعني a minus b, but the sign of the middle term is plus. يعني if this is negative, the middle term, the sign is plus. Here is يعني anytime you look at an expression and you're trying to factor it, see if you have a formula that you can apply to factor the expression. طبعا the idea of factoring expressions is that we will be looking at equations. An important topic in algebra is try to solve equations, and one way to solve equations is by trying to factor equations. We will apply all these methods to factor expressions to help us solve equations. Let's look at an example of factoring by grouping. This term here, this expression has four terms: 30ax plus 150a plus 20cx plus 100c. First, let's see if there's a common factor to all four terms. You can see that the coefficients has a common factor which is equal to 10, so we start by factoring 10 from the four terms. You can write this as 10, and you factor out the 10. You're left from the first term, you're left with 3ax. From the second term, you're left with 15a. From the third term, you have 2cx. And from the final term, you have 10c. Next, we would like to see the terms inside the bracket. There is no factor that's common to all four terms, so we will see if we can group. يعني we will try to group 2 and 2. Take 3ax plus 15a, take these together, plus the second two terms are 2cx plus 10c. Now take, for the first two terms, there is you can take the 3 as a common factor. The coefficients 3 and 15 have a common factor, which is 3. and the variable terms have a common factor which is equal to a. So you can factor 3a. From the first term you're left with x. From the second term you're left with 5. Now we move to the second second group, which is 2cx plus 10c. You can factor the 2 and the c. The 2 and the c are common to both factors. Factor 2c. From the term 2cx you're left with x, and from the term 10c you are left with 5. Now for this expression you have two terms, 3a times x plus 5, that's your first term, plus the second term, which is 2c times x plus 5. There is a common factor, which is x plus 5. So now you can factor the x plus 5. طبعا you have a 10 outside the big bracket. Factor the x plus 5. If you factor x plus 5, from the first term you're left with 3a. From the second term you're left with 2c. So here is your final product. يعني the original expression now is written as the product of three factors, 10 times x plus 5 times 3a plus 2c. The second example, we will look at a trinomial, يعني an expression that have three terms, and see if we can use a formula to factor it. 9x squared plus 6x plus 1. Note that the first term is just the square of 3x, and if you take 3x and square it, you get 9x squared. The middle term is just 2 times 3x plus 1. So you can write this as a perfect square. This is 3x plus 1, everything squared. طبعا you can always check your answer if you square 3x plus 1. يعني if you square that expression, if you take 3x plus 1 squared, you should get 9x squared plus 6x plus 1. Another example of factoring a trinomial is try to write it as a product of two brackets. And here is where you may have to try one thing. If it doesn't work, this is the try and error method. What we are trying to factor is 2x squared plus 11x plus 5. We want to write this as a product of two factors, two brackets. The way to look at that, you want طبعا the variable terms, يعني each bracket, the first term is the variable. We want the product of the first terms to be 2x squared. So we can try 2x and x. Certainly the product of 2x and x will give us 2x squared. Now the product of the second terms should equal to 5. So we can try 5 and 1. Certainly 5 times 1 is equal to 5. But we have to check to make sure that the middle term will work. Here the middle term, you have to multiply the outside terms, 2x times 1, and add it to the product of the inside terms, 5 and x. If you take 2x times 1, that's 2x, plus 5x, you get 7x. So the middle term doesn't work. يعني this will not work, so we have to try something else to factor the same expression. Again, 2x and x will still work. 2x times x is 2x squared. But instead of writing 5 in the first bracket and 1 in the second bracket, we will reverse the order. We will write 1 times 5. Now this factorization should work. 2x times x is 2x squared. 1 times 5 is equal to 5. And then the product of the outside terms, 2x times 5 is 10x. Add this to x, which is 1 times x. The sum will be 11x. This factorization will work. Here are more examples of using the formulas. If you have x squared minus y to the 4, طبعا the idea is to try to write it as the difference of two squares. You can think of y to the 4 as y squared, everything squared. So that is the difference of two squared. Yani the first term is x, and that is squared, and the second term is y squared, and when you square that, you get y to the 4. So you can write the factorization using the formula. Take x minus y squared, I need the first term minus the second term, times x plus y squared, which is the sum of the two terms. An example of using the sum of two cubes is 8z cubed plus 27. طبعا you can think of the first term to make this as the sum of two cubes. The first term is just 2z everything cubed. The second term is just 3 cubed. So this is the sum of the cube of two quantities. طبعا the first quantity is 2z and the second quantity is 3. For applying the formula, then you can factor this as the sum of the two terms, yani 2x plus 3, then the square of the first term, which is 4x squared, minus the product, which is minus 6x, plus the square of the second term, which is 9. And as usual, you can always check to see if your factorization is correct. By multiplying the factors, you should get the original quantity that you started with. One more example of using, now in this case it is the difference of two cubes, 125y to the 6 minus 1. You can think of this as the difference of two cubes. 125y to the 6 can be written as 5y squared everything cubed. And if you take 5y squared, cube that, you will get 125y to the 6. And of course 1 is just 1 cube. For applying the formula for the difference of two cubes, you take the difference of the two terms and you take 5y squared minus 1, then the square of the first term, that will give you 25y to the 4, plus the product, which is in this case it will be 5y squared, plus the square of the second term, which is equal to 1. طبعا all of these formulas, and factorization is a skill that you can always improve by practice. You should try to do as many examples as you can so that you can factor. As you can see, that there's different ways to factor depending on the term or the expression that you start with. Here is another method to factor using substitution. And the idea of substitution is that if you have a term, if you can make a substitution that will result in a form that you recognize, that you can apply one of the formulas, then you can go ahead and factor, and then to substitute back you will get a factorization in terms of the original expression. And here is also طبعا when you have four terms, you can factor the four terms. You can take them 2 and 2, or as an example 2, we'll see that sometimes you can take 3 terms and 1 term. Group 3 terms together and 1 term together. The expression we're trying to factor is y squared plus 10y plus 25 minus z squared. So what we will do, we will group the first 3 terms together, and then 1 term will be left alone. The first 3 terms form a perfect square trinomial. The first 3 terms, y squared plus 10 plus 25, is a perfect square trinomial. So you can write it as y plus 5 everything squared minus the fourth term, which is z squared. Now here is where the substitution can be applied. You can this looks like the difference of two squares, so your substitution take y plus 5 to equal another variable, call it u for example. Replace y plus 5 by u. So this expression now, the expression we have is y plus 5 squared minus z squared. Replace y plus 5 by u. We have u squared minus z squared. Now you have the difference of two squares. So you can write this as u plus z times u minus z. The last step now, you want to substitute back, replace u by y plus 5. So your final factorization will be u is just y plus 5, then you have plus z times the second bracket, replace u by y plus 5, so you have y plus 5 minus z. So now your final factors are in terms of the original variables. You have written your original expressions as a product of two factors. Next, we would like to see how we can factor negative terms, and also we will look at rational exponents, how to factor rational exponents. If you have an expression where you have a common factor, the variable factor is raised to a negative power, or a rational exponent, you can factor out the variable raised to the smallest exponents. And the exponents that you want to factor is the variable raised to the smallest exponents of all the terms that you have. Exponents on variables within parentheses are found by subtraction. And that's how, once you decide what your factor is, which is the smallest power, you can find the remaining terms by subtraction. And let's look, for example, at this expression, which has negative exponents. 7 times z to the minus 8 plus 6 times z to the minus 7 minus 5z to the minus 6. Here the smallest exponents actually is minus 8. So what you want to factor is z raised to the smallest power. You want to factor z to the minus 8. Now the way to find this is your common factor, z to the minus 8. So this is the factor, so this is multiplied by, when you factor z to the minus 8 from 7z to the minus 8, the power that's left is just minus 8 minus minus 8, so it's 0. So your first term is just 7 times z to the 0, or just 7. Now for the second term, when you factor z to the minus 8 from 6 times z to the minus 7, the power that's left is just minus 7 minus minus 8, so the power is 1. For the third term, you are factoring z to the minus 8 from 5z to the minus 6. The power that's left is just minus 6 minus minus 8, so you're left with 2. It's easy to check that the factorization is correct. If you multiply z to the minus 8 by this expression, you should get your original expression. It's a bit may look different, but when you're factoring in negative terms, you have to be careful. The result, you're factoring in negative terms. That's how you decide the terms that are left from factorization. That's how you figure the power of each term. Of course, this step here we factored z to the minus 8. Just to rewrite the expression, z to the 0 is just 1. So the first term is 7. Z to the 1 is just z. And of course, z squared, you can just leave it like it is. So this is your factors. If you would like to not look at negative exponents, the negative exponents can always be written in the denominator. So that same expression can be written as 7 plus 6z minus 5z squared. The negative factor, z to the minus 8, can be written in the denominator as z to the 8. I think this is the final section in chapter R. We will look at rational expressions, and whenever you're dealing with rational expressions can have polynomials. That's what a rational expression is. It's a quotient of two polynomial. And also we will look at radicals. With radicals, these are expressions that have a power equal to a fraction. this is a topic that we will cover. First of all, the definition of a rational expression is a ratio of two polynomials. Anytime you have a quotient, you have to worry about the denominator not equaling 0. The values of the variable that makes the denominator equal 0 are called restricted values of the variable. That means you cannot use those values in that expression because they will give you 0 in the denominator, and you cannot divide by 0. So these are excluded. Again, a restricted value is a value that will make the denominator equal 0. Here is an example of a rational expression. X plus 5 divided by x plus 7. This is a rational expression. Now, what are the restricted value of this expression? The value that will make the denominator equal to 0, طبعا x plus 7 is equal to 0 when x is equal to minus 7. The restricted value is equal to x, يعني x equal minus 7, this has to be excluded. So for any time you look at an expression like this, the restricted value cannot be allowed, so we cannot allow x to equal minus 7. And this expression is used provided that x does not equal minus 7. Now, sometimes we have to work with rational expressions. So how do you simplify a rational expression? You can simplify a rational expression by trying to cancel factors that are common to both the numerator and denominator. When you do this, you have an equivalent term. For example, if you have the rational expression a times c divided by b times c, c is a common factor, so you can cancel the c, and the result is a over b. So this equality means the expression to the left, ac divided by bc, is the same expression as a over b. We got this expression to the right by canceling the common factor. And remember, these are rational expressions. B cannot equal 0, and also c cannot equal 0. These are restricted values. This works if the factors are numbers or if they are algebraic expressions. So you can always simplify an algebraic rational expression by canceling the common factors. Here is a more complicated example. Suppose you have 2x squared minus 9x minus 5 divided by 6x squared minus 30x. In order for us to see if there is a common factor or not, the first step is to factor each expression, and factor the numerator and also factor the denominator. The numerator 2x squared minus 9x minus 5 can be factored as 2x plus 1 times x minus 5. The denominator, 6x squared minus 30x, you can factor the 6x, and you're left with x minus 5. And you notice that there is a common factor. X minus 5 is a common factor to the numerator and denominator. So you can cancel that. So you're left now with 2x plus 1 divided by 6x. Now remember that the original expression, there is two restricted value. X cannot equal 0, and also x cannot equal 5. After you simplify, to get the equivalent form, those two restricted value remain restricted. 2x plus 1 divided by 6x, this is the equivalent form for the original expression. You still have x equals 0 and x equals 5 as restricted values. In this expression, x does not equal 0 and x does not equal 5. You may say that for this, after you simplify, x does not seem to cause a problem, but it is a restricted value in the original expression. It continues to be a restricted value after you simplify the expression. Our original expression is equal to 2x plus 1 divided by 6x. The restricted values are 0 and 5. Next, we would like to see how you can multiply and divide rational expressions. We are probably more familiar with how to multiply and divide fractions. Fractions are rational expressions, but all the formulas that we know about numbers also work for algebraic expressions. So we will see how to multiply and divide rational expressions. The first formula, to multiply two fractions, and to multiply a over b times c over d, you multiply the top part and you multiply the numerator, a times c, divided by the product of the denominator, which is b times d. And طبعا you need to take care of the restricted values. For b and d cannot equal 0. It's a simple way to multiply two fractions. Just multiply the top part divided by the product of the lower part, the denominator. Now what about division? This works for fractions, numbers, and also works for expressions. For a divided by b, that's a over b is your first rational expression, divided by c over d. The way to do this, you just write the first expression like it is, a over b. The division becomes multiplication, and then the second fraction, the fraction that you are dividing by, you invert that. For a over b times c over d, if you invert it, it will become d over c. This is the rule we know about numbers, which also works for algebraic rational expressions. So here is an example. The first rational expression is 12 minus 3x divided by 2x plus 1. You want to divide this by the second rational expression, x squared minus 3x minus 4 divided by 2x squared plus 15x plus 7. Now you can just the first expression is you leave it like it is, but you can go ahead and factor. From the numerator you can factor 3, and you're left with 4 minus x divided by 2x plus 1. The division becomes multiplication, and then you invert the second expression. The denominator, 2x squared plus 15x plus 7, becomes the numerator, and that can be factored to 2x plus 1 times x plus 7. The numerator in the original expression becomes the denominator, and it can be factored to x minus 4 times x plus 1. Now, since this is a product, you can cancel the common factors, and any factor that is common to both the numerator and denominator, you can go ahead and cancel it. First of all, here you have 4 minus x, and this is x minus 4. The difference is just minus 1. And if you cancel x minus 4, you're left with minus 1. There's also another common factor, which is 2x plus 1. You can cancel it from the numerator and denominator. So you are left with, the negative sign, you can write it in front of the result, the fraction. So you are left with minus 3 times x plus 7 divided by the only factor left in the denominator, which is x plus 1. if you remember the rules about multiplication and division for numbers, the same rules apply. when you're working with algebraic expression, you want to apply these rules, try to factor, and then cancel common factors, and that will simplify your original expression. And the result of this division, in this case, will be minus 3 times x plus 7 divided by x plus 1. Now, what about the operation of subtraction? It is done addition and subtraction. Subtraction is just a special case. For addition, if the two fractions have the same denominator, that's easy. If you add a over b plus c over b, these have the same denominator. The sum is equal to a plus c, and you add the numerator divided by the common denominator. But the result is a plus c divided by b. The same thing for subtraction. If they have the same denominator, a over b minus c over b is just a minus c divided by b. Here in all those cases, all the fractions, the restricted value is 0. B cannot equal 0. This works طبعا for numbers, and it also works for algebraic expression. Now this is the case if you have the same denominator. If the two fractions have different denominators, what you want to do is try to rewrite them so that they have the same denominator. Here is one way to do this. Suppose I want to add x divided by x minus 1 plus 2 over x. طبعا these do not have the same denominator. What you want to do is take the first rational expression, or the first fraction, multiply both the top and bottom by the denominator of the second fraction. Yani take x over x minus 1 and multiply both the top and bottom by x. Now for the second fraction, multiply both the top and bottom by the denominator of the first fraction. Yani multiply 2 over x, the top and bottom, by x minus 1. If you do this, then the resulting expression will have the same denominator. And here in this case, both denominators are x times x minus 1. Since these have the same denominator, the sum here will be just x times x, which is x squared, plus 2 times x minus 1. The denominator, the common denominator, is just x times x minus 1. The only thing left now is to simplify the numerator by multiplying 2 times x minus 1. So the final result will be x squared plus 2x minus 2. The denominator is x times x minus 1. Another method to accomplish the same thing is to if you are adding two fractions with different denominators, you can perform the addition by rewriting the expressions so they have the same denominator. Or an equivalent method is to multiply both the top and bottom by the same factor so that you end up with the same denominator. Let's see how to add or how to simplify this expression. This is what we mean by a complex fraction. And you have a rational expression. The numerator involves the sum of two fractions, and so is the denominator, also is the sum of two fractions. How do you simplify an expression like this? The numerator is 1 over x plus 1/2. The denominator is 1 plus 2 divided by x. Start with the numerator. Try to take a common denominator for those two fractions. 1 over x, you should multiply both top and bottom by 2, which is the denominator of 1/2. 1 times 2 divided by x divided by 2, x times 2. For the second fraction, multiply both top and bottom by x, which is the denominator of the first fraction. Multiply 1 by x, this is divided by 2 times x. The result of doing this, like we did before, you get the fractions in the numerator have the same denominator, which is 2x. So you just add 1 plus 2 is equal to 2, plus 1 times x, which is x. Now you move to the denominator and try to do the same thing. The denominator is 1 plus 2 over x. You can think of 1 as 1 divided by 1. So multiply both top and bottom by x. 1 times x divided by 1 times x. For the second fraction, you don't need to do anything. just write it as 2 over x. Now you still have the same denominator. For the result of the numerator, you have x and then add x plus 2. Now how do you still, we're not finished. You can think now of this expression as 2 plus x over 2x. That top part is divided by x plus 2 over x. فطبعا the division, write the first fraction 2 plus x over 2x. The division becomes multiplication, and invert the lower fraction. For x plus 2 over x would be written as x divided by x plus 2. The next طبعا you want to cancel common factors. So you can cancel 2 plus x with x plus 2, and also cancel x with, and you have here 2 times x, so you can cancel the x, so you're left with 1 in the numerator and only 2 in the denominator. For any time you have a complex fraction, start by simplifying the top part, the numerator, and simplify the lower part, and deal with this as a division, the division of two rational expressions. We will do the same problem, but this time we will use another method. Again, the idea is still the same, as you are simplifying the top part and the bottom part, and you end up with by simplifying the top part and bottom part, you'll be able to simplify the entire expression. But this is the same example. This time we will not take the numerator and denominator separately. This time we will look at a common, here the greatest common factor for 1 over x plus 1 over 2 is 2x. So if I multiply the top and bottom by 2x, طبعا again you can think of the numerator, 1 plus 2 over x is the same as 1 over 1 plus 2 over x. So again they have, x is a common factor. For the original expression, if I multiply the top and bottom by 2x, which is the least common multiple of the two denominators, the result will give us a simple expression. So again, because we're multiplying the top and bottom by the same factor, we are not changing the original problem. Now 2x times 1 over x, you can cancel the x and you're left with 2. And 2x times 1 over 2 will give us x, and you cancel the 2, you're left with x. Now let's do the denominator. 2x times 1 is just 2x, plus 2x times 2 over x, cancel the x, and you're left with 2 times 2, which is 4. This is طبعا a much simpler expression, but we still should look to see if there is a common factor. For the denominator, if you factor the 2, you're left with x plus 2. The fraction now is 2 plus x divided by 2 times x plus 2. You can cancel, you have a common factor, which is 2 plus x. If you cancel that, you're left with 1 over 2. The final, I think, slide, we will, this is yet another way to طبعا simplify rational expressions. In this case, we want to work with, if you have an expression where you have a radical. For example, 5 divided by the cube root of 2 times y squared. Now the idea of rationalizing the denominator is to rewrite the expression in a way that the denominator does not have a radical. This is called rationalizing the denominator. If I want to start in example 7, I have 5 divided by the cube root of 2y squared. I want to rewrite this expression so that the denominator does not have a radical. The trick to do this is to, again, you have to multiply the top and bottom by the same factor. Now, to get rid of the cube root of 2y squared, I have to multiply it by another cube root, but the expression under the cube root has to be such that when I multiply it by the expression under the cube root of the original fraction, I end up with an expression that I can take the cube root for. So here, if you look at this, مثلا you have the cube root of 2y squared. The factor that has 2, I have to multiply it by 2 squared. This way now when I multiply the 2 times 2 squared, I get 2 cubed, and I can take the cube root of that. Now for y squared, I need to multiply it by y, so that the product will be y cubed, and I can take the cube root of that. So our original expression again is 5 divided by the cube root of 2y squared. I want to multiply both top and bottom by the cube root of 2 squared times y. And again, it's important to know that you have to multiply both top and bottom by the same factor. Now this is a product of cube roots, the denominator. I can write it as the cube root of the product. So this is the cube root of 2y squared times 2 squared times y. 2 times 2 squared is just 2 cubed. Y squared times y is y cubed. The numerator, you just multiply 5 times the cube root of 2 squared y, which is 5 times the cube root of 4y squared. But now look at the denominator. This is the cube root of 2 cubed times y cubed. You can simplify this by taking the cube root of 2 cubed, which is 2, times the cube root of y cubed, which is just y. Here is the final result. This is the same expression. This is equivalent to the expression I started with, but now the denominator does not have a radical. And this is what we mean by rationalizing the denominator, is to rewrite the expression so that it does not have a radical in the denominator. Now another situation where you want to rationalize an expression that have radicals is this example. Example 8. We want to rationalize the denominator. The expression here is 8 divided by the cube root of 13 minus the cube root of 11. To get rid of the radicals in the denominator, remember the formula we had. If you multiply a minus b times a plus b, the result is a squared minus b squared. And that will enable us to get rid of the square root. The trick here now is multiply both top and bottom by the same expression that's the denominator, but instead of minus, change it to plus. The square root of 13 minus the square root of 11, you multiply it by the square root of 13 plus the square root of 11. And you have to do this both to the top and bottom. Our original expression now becomes 8 times the square root of 13 plus the square root of 11 divided by the square root of 13 minus the square root of 11 times the square root of 13 plus the square root of 11. This part that's in blue, I multiplied the original expression by the same factor. And that factor is just the denominator with the sign, the minus sign becomes plus. But now what happens in the denominator? This is like it has the form a minus b times a plus b. The product will be a squared minus b squared. 13 squared is just 13 minus the square root of 11 squared is just 11. The numerator, you have to multiply 8 by the square root of 13 plus the square root of 11. The denominator, 13 minus 11 is just 2. 2 has a common factor with the 8. You can cancel 2. So your final answer should be 4 times the square root of 13 plus the square root of 11. Just to finish this tutorial, like everything else we do in this course, this is algebra. You are working with different types of expressions. There are different things we are applying. Those different formulas and different ways to work with rational expression or factoring. All this requires practice, and your book have many exercises and examples. In order for you to learn these techniques, you need to practice. You need to solve as many problems as you can.